Okay, so last day we started and didn't finish a set of notes, and we'll probably do the same thing today. Just so you guys are aware, I'll do my best to try to keep this to about an hour or less because I know your attention spans will start to wane by the end. But these three lessons are all kind of meant to go back to back to back. Okay, so I don't expect you to do a lot of your like practice work until we do all three lessons. Does that make sense? So I'll do my best to hopefully finish by like say 22 or 20 after, so that it's only just about an hour. So let's recap what we learned yesterday and we'll add to it. Last day we learned about what makes something a standard position angle. Okay, a standard position angle means that if you had like say like a circle like this, we're going to always start our angle from the center of a grid. That's one of the vertice points of a triangle. We're going to put one of the arms always along the positive x-axis. You might ask why. And I think historically the rationale basically was the sun rises in the east. And so this is east effectively. Does that make sense? And the sun rises in the east, and as the sun rises throughout the course of the day, eventually gets to like say right overhead, that's midday, say noon roughly, depending on where you are. And eventually the sun will then set over here, and this is now the west, and now the sun has set. Does that make sense? I think that's historically the only reason why 0 degrees literally starts over here. But the good news is that our sun keeps rotating. It's actually us that rotates, not the sun. But from our perspective, the sun keeps moving. It goes on the other half of the earth, and then it starts again for the next day. Does that make sense? And so I showed you the idea that we can basically measure any angle we like. And degrees is the most common type of angle that you guys need to be familiar with. And I think degrees is nice for two reasons. One, it's pretty easy to estimate degrees. If I asked you to draw me like say 20 degrees, most people would probably be able to say that like 20 degrees is maybe like about that much of an angle. If I said to draw 93 degrees, you'd go, okay, well 90 is straight up, so 93 might be like that. Here's the problem though. Degrees to some degree are arbitrary. Okay. They've just been randomly chosen that a full circle is 360 degrees. Why? For what rationale? Other than the fact that 360 divides by like almost every number and it's more or less 365 days in a year, there's really no purposeful reason for why 360 degrees is a circle. The more official way of measuring angles is known as a radian. Okay, can you close that door on the way out, by the way? So I think we're going to hit a bell in a second here. So the way a radian works is that 1 radian is where if I were to draw this out, 1 radian would basically be where I draw one line right here, I draw another line right here. Those are both the same distance because they're both radiuses in a circle. And the distance around the edge is the exact same amount. So if this is 3 units and this is 3 units, then the edge is also 3 units. And we learned last day, and really there's not much to do yet, by the way. If you feel like, if I asked you to do something yesterday and you feel like you couldn't answer a question, by the way, that's kind of fine. Like I haven't actually given you any purposeful questions to answer yet. I'm mostly just explaining theory. Does that make sense? So please don't feel like I don't know what I'm doing. Like I haven't even asked you to do anything yet. Okay. But I lost my train of thought. What was I going to say? One of the things that hopefully you guys are able to work with then is the idea that any one of these angles can actually be measured in fractions of pi. And that's a really new concept because basically the idea is if all the way around the circle is 360 degrees, all the way around a circle in terms of how many radians you have is 2 pi worth, which is 6.28. And I showed you guys a slide where you can fit exactly 6 plus a little bit more of a slice of pizza in like a circle. And because of that, I need you guys to start becoming more familiar with the idea of measuring an angle as something like this. Rather than calling it 30 degrees, we call it pi over 6. Or rather than calling it 45 degrees, we call it pi over 4. And the more we practice this, the more fluent you're going to get. If you guys are okay with the idea that all the way around the circle was 2 pi, if you can follow that train of thought or at least accept it, then halfway around the circle is pi radians. Then you just start breaking things up into fractions. Like say 90 degrees. 90 degrees is, if this is pi, well then this is half of pi. Does that make sense? So 90 degrees is now going to be called a pi over 2 radian. And right here, 45 degrees, so you can fit like, I'm going to break things up into quarters. Here's your first quarter, your second quarter, your third quarter, your fourth quarter. Each quarter of pi is worth 45 degrees. And you might say, Chris, why is this useful? Like, this seems like the dumbest thing in the world. But I actually have a couple of uses for it, and I didn't get to finish that yesterday because I ran out of time. But I'm hoping today I can try to show you some reasons why measuring things in radians is useful. The first one is that you can always have a radian measure as a exact value as a fraction rather than as some sort of decimal number. For example, let's say that I gave you 17.895 degrees. We can write this as fractions of pi. Here's how you do this. And I was doing this at the end of last class. The conversion ratio is that for every 2 pi in radians, you get 360 degrees. You guys remember doing this kind of towards the end of last day? I wanted to show you this on my calculator, but it froze, so I fixed it yesterday. So here's what I'd suggest you do then. Take 17.895 times by 2. Don't times by pi, just times by 2. Divide by 360, and then turn that into a fraction. Dang it. Okay, let's not pick that number. Let's pick, well, your calculator gives up after a certain point. We can do this in calculus, but I don't want to show you calculus right now. So let's pick something that will work. 17.85. 17.85 times by 2 divided by 360. This should work. I'm going to turn that into a fraction. There we go. The only reason your calculator didn't do it is because after a certain point, it gives up and doesn't want to handle like a fraction that's too large. What we could then say is that this is 119 over 1200 pi as like a fraction. And we could then go back to the circle and try to figure out, well, what is 119 out of 1200? 119 is almost like 120 out of 1200. It's one off. Does that make sense? And then 120 out of 1200, if I hack, like, say, that off right there, 12 out of 120, you're talking a tenth, right? So what I'm saying we need here is a tenth, 1/10 of pi. Almost a tenth of pi, just slightly off, right? Well, if I had to break this circle up into tenths, I can now do that. This one right here is currently broken up into things like sixths and quarters and thirds, but if I want to break it up into tenths, right here, I did it like this. If this was, say, 10 tenths of pi, then like right here would be 5 tenths of pi. Does that make sense? Well, then this would be broken up into fifths. More here. Here's my first tenth, my second tenth, my third tenth, my fourth tenth, my fifth, 6, 7, 8, 9, 10. But if we said we needed basically 1/10 of pi, 17 degrees is more or less this angle right here. So long story short, we should be able to convert a degree into a number like this, where it's all about how many fractions of pi you have. And then we can be very exact. And all it takes is enough time to basically keep cutting things in halves and halves and halves. Does that make sense? Okay, here's the second reason why. I want to hop to the next word problem right here. One of the things we can do with this is we can calculate, using radians, what's known as an arc length. Okay. I showed you guys this in class the other day. An arc length is basically this distance right here. And if we know the distances here and here, we can calculate an angle, but we can also calculate an arc length working backwards. So I'm going to try this first example here. We're going to be asked to find this angle right here. Well, what we can use is the definition of a radian to solve this puzzle here. I wrote up here, a radian is defined as how many arc lengths you have in a radius. Okay. For example, if this was 20, and if this was 20, and if this was 20, this right here would be 1 radian. Does that make sense? But it's not. This is 20 and this is 20, but this is 45. Is it going to be 1 radian? Is it going to be 2 radians? It's going to be like 2 and a bit of a radian. Does that make sense? The reason why is that if they were all 20s, if this was 20 and 20 and 20, you'd have 1 radian. If this was 40, you'd have double the arc length to the radius, then it would be 2 radians. But because it's 45, we have roughly like 2 and a bit radians. So I'm going to calculate exactly how many radians I have right here by doing this. The way you solve for an angle is that it's how many arc lengths you have divided by radius. The arc length that we had was 45 centimeters. The radius we had was 20 centimeters. So if I divide those by each other, it'll tell me how many radians I have. So there are 2.25 radians. There, I've now solved for that angle right there. Does that make sense? Now, that on its own is not all that useful necessarily, but I want to show you how to do the opposite operation because this is useful. Let's say I give you this thing right here. I'm going to tell you to measure this out in 50 degrees. I'll go with degrees to make it simple at first. And then I'm going to tell you that the radius is 16 centimeters. My question is, how big is this right here going to be? How far along the edge? Does anybody remember roughly how big a radian was in terms of degrees? Well, there's 6.28 in a full circle. 1 radian is about 57 degrees. Good job, yeah. So if this is going to be slightly less than 1 radian, then it means that my guess is that this distance along here is probably going to be about 14 or 15 centimeters because it's slightly under a radian, but I want to prove exactly how far it is. So here's how I'm going to do that. I'm going to use the exact same formula that your angle in radians is your arc length over your radius. Only in this example here, what I'm trying to solve for is my arc length. So to algebra this equation slightly differently, I'm going to times the radius up and go, my angle times by my radians is my arc length. Okay, well, what's my angle? But it's in degrees. I can't use 50 degrees. The way this formula works is it has to be in radians. But I just showed you guys and reminded you a few seconds ago how to convert degrees to radians. If you have 50 degrees times by 2 pi divided by 360, that'll get you radians. Now, the way I like to do it, though, is I take 50, I times by 2, I don't times by pi, I divide by 360, and I make it a fraction, and I end up getting 5/18ths of a radian. Sorry, 5/18ths pi of a radian. Does that make sense? Yeah, 5/18ths times pi. That's what my angle is going to be. And then I'm going to times that by my radius. And the radius was 16. So I'm going to take 5 pi over 18. That's my new angle. I'm going to times by my radius of 16. And I got a final answer here of 13.9626, etc. But hang on a sec here. We don't like rounding, because that was kind of the whole point of yesterday. Did you guys get 13.9626? When you took this number right here, you did 5 pi over 18, not just 5 over 18? And then times by 16? Over 18 times 5. You times by pi a second time, though. You need 5 over 18 times by pi, and then also times by 16. So I ended up getting 13.96. Anybody else not get 13.96? Okay, but here's the problem. That is a rounded number. I want to leave it as an exact value. So one of the ways I can do that is to make it an exact value. I'm just going to take this guy right here and try to simplify it as much as I can. Rather than actually timesing 5 pi divide by 18 and times by 6 and get a decimal number, why don't I reduce this and say these guys both divide by 2. I'll make that 8. I'll make that 9. I have an exact value of 40 over 9 pi. That is exactly how far this arc length is right here. Does that make sense? Let me show you that one more time here. I took my angle, I times it by my radius. But my angle had to be in fractions of pi. So I took 50 times by 2 divided by 360, and I ended up with, before I was scribbling all over it, I'll go back here. Before I scribbled all over it, I ended up with this angle was 5 pi over 18. Everybody okay with me getting that angle? Then the way the formula works is that your radians is your arc length over your radius. So if you want to find your arc length, times by your radius. So take your angle times by your radius, you get an answer. Problem is the answer is a rounded number. I'm going to need to round it at some point. So if we want to practice working with exact values, I'm going to take this value right here, which was 5 pi over 18. I'm going to times it by 16, and I'm just going to leave it like that. The only thing I'm going to do then is just simplify it a bit. So my simplifying was to say 5 and 18, they don't divide, right? 16 and 18, though, you can reduce 16 and 18. Divide them both by 2. 16 divides by 2 to give you 8. 18 divides by 2 to get you 9. 5 times 8 is 40. There. This is my exact value as to how far it is around the edge. And now I don't have to round it. I said it was 13.96. Let's just double check here. 40 over 9 times pi is 13.96, but rather than writing it as this bit right here, leave it as that. I lose you there still? You okay? Okay. I just don't want to move on if you're lost, so you're good? Okay. Okay, so let me try a question. By the way, dash 130-1, this is an old diploma question. So here's the here's the kind of the question. You're supposed to figure out the total length of the sidewalk. What they've given you here is 97 degrees around a baseball diamond in like the corner here. And you've got two sides like this, both 30 meters. And then there's this curvy section right here. The final answer to this is going to be 30 plus 30 plus your arc length. Does that make sense? Because you're going to walk 30 here. You're going to walk 30 here. But what we don't know is how far it is around the edge. Now, I mean, granted, who cares that you do it exact? But that's why radians could be useful, is that radians could get you an exact number. Not a rounded number, but like very precise. The answer is going to involve pi as part of it. Does that make sense? So here's how you solve it. First of all, this 97 degrees, not useful to us. Degrees is very helpful in a lot of places, but going forward in math, it's better to put it in radians. So I'm going to take 97 degrees. I'm going to times by 2 pi, divide by 360. So 97 times 2 divided by 360 gives me, well, I have to put it in a fraction. I got 97 180 fractions of pi. Everybody else get that? Okay, let's talk about that for a second, because sometimes it takes a while to wrap your head around what we just discovered. 97 over 180. What if it was 90 over 180? 90 over 180 would be half, right? That makes sense. 90 over 180 would be half. Well, if I were to draw you a circle and start here, where is 1/2 of pi? This is pi right here, right? 1/2 of pi would be right here. This is where 90 over 180 pi would be. This is where 180 over 180 pi would be, because that's the full pi. So if we have 97 over 180 pi, it means that we're slightly further. Wouldn't that basically be 97 degrees? Can you kind of see how like that relationship fits together a bit? If you can interpret what a radians is, and the more you do it, the better you get. This right here is now going to get used in my formula. So my formula was arc length divided by radius is how we define a radian. 1 radian is when the arc length is the same as the radius. So if I want to solve for the arc length, I take my angle and I times by my radius. Okay, I don't use my angle in degrees, I use my angle in radians. So my angle needs to be 97 pi over 180. That's my angle. And then my radius is 30. Because that's this side or this side right here. Now, if I had to do it with an exact value, I would just skip typing in pi and I'd find a fraction. But why don't we go with a decimal number, because it does say to round to the nearest meter. So 97 pi divided by 180 times by 30. I got 50.789. So if I have to round that to the nearest meter, it means that around this edge right here was 50.789 dot dot dot, but let's call it 51 meters. So the final answer would have been 30 plus 30 plus 51, which would be 111. But that's because we were allowed to round. Okay. If we weren't going to round, hopefully you guys would agree, though, that we do have a way of trying to take this exact value right here, and we could have written it in fractions of pi. Hey. Good. What's up? Sorry. Okay. Did Okay, here's what I like to do on my last slides here. Now I want to try to put this all together. Okay. So if you feel like up until now we really haven't done anything, this is a very typical question I might ask you. Okay. I might ask you, tell me the exact ratio for cosine 30 or tan 210 or something like this. Now, in your graphing calculator, you could just type in cosine of 30 and get a number. So you get a number like that. Or you could type in the tan of 210 and get a number. And you guys have been doing this before at other points in your trigonometry lives. But now putting all of the information I've taught you together at a time, we should actually be able to find a way to take this number right here, and rather than having it be a rounded decimal number, we should be able to write it as something irrational. So I'd like to put this all together. So this would be kind of like the first sort of task where I'd like to actually be able to do something. So here's the first thing we need to do. We need to plot our angle on a standard position triangle. So 30 degrees is very simple. 30 degrees is going to go right about here. Does that make sense? I'm going to put one arm along this axis. I'm going to put one arm along this axis over here. I'll fill in the blanks and kind of make it a triangle. And right here, this is going to be 30 degrees. Now, if you guys remember from last day, I showed you two triangles that were known for their exact values. One of them was called a 30-60-90 triangle, and one of them was called a 45-45-90 triangle. Do you guys recall those at all? I know it was only yesterday, but does that ring a bell? I'm going to go back in my notes a little ways here and try to find it. Or maybe I won't. Give me a sec. Ella. She is in Scott's room, who's in Lab's room right now. Okay, I'm back. All right. Can you guys see, at least back in my notes right here, this triangle right here? What I'm going to do is I'm going to transpose this triangle that I have right here. I wish I could literally cut and paste it, but I'm going to transpose this directly onto my other slide. So I'm going to remember that 30 is in this quarter here, 60 is up here, and it goes 1, 2, root 3. So try to remember that. 30 was in this corner here, 60 was in this corner here, and it went 1, 2, root 3. Everybody okay being able to do that from our previous slide there? Okay, well, let's talk for a second about what cosine means. You guys learned in previous trig courses SOHCAHTOA, right? Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. So cosine is supposed to be adjacent over hypotenuse. If this is the angle we're talking about right here, this 30 degrees, which side is the adjacent side on that triangle? Root 3. So the adjacent side is the root 3. Which side is the hypotenuse? 2. Well, now what I've done is I have an exact value answer. And that's kind of the whole goal of trigonometry. From grades 1 to 10, we're totally cool if you round. Grades 11 and 12, stop rounding. Does that make sense? Now in physics and chemistry, we sometimes use angles. But what we'd prefer to do is rather than typing in our calculator cosine of 30 and using this decimal number right here, it's preferred to call it root 3 divided by 2. Can you guys see how that's the exact same number? Only this is exact. Now, there's not a lot of places in life where this really, really matters. Okay? But hopefully you can agree there are some places, like say the famous story is spaceships going into outer space. Slight rounding errors are catastrophic if you're trying to send a space rover between here and Jupiter, right? Because if you're off by even the slightest amount of angle, eventually it's just going to get wider and wider and wider and miss by the time you're there, right? So to the best of your ability, you always want to do things as exact as possible. Does that make sense? That's what I'm trying to show you the big picture of here now, is that every time in the past when you typed in, say, sine of 80, you've just been content to let it just be some decimal number here, right? But what we want to start to try to do is recognize that we can actually turn it into a fraction like this. So let me try another one here. Tan of 210 degrees. So first thing we should do is we should plot on a grid where is 210 degrees going to be if it's in what's considered to be a standard position. Well, the first arm is definitely going right here, because that's just by default what we say. Where's 210 degrees going to end up? Which quadrant? Yeah, the third one. 210 degrees is going to be kind of over here. Does that make sense? Because 180 was about right there. 90 is about right here. So 210 is sitting somewhere down here. The problem is, how do I make a triangle out of this? Well, I showed you guys that last day as well. We always make what's known as a reference triangle, which is where we always draw the triangle back to the axis. So I'm actually going to draw a triangle like that. Or I draw it back up like this. What's the reference angle on a triangle that is 210 degrees? Yeah, this is 30, which is convenient. So I'm going to actually start plotting 30 degrees here and 60 degrees here. And I'm going to start plotting 3 sides again. And it's going to be the same 3 sides that were on this triangle right here, only now it's in a new quadrant. But I need to show you one little change here. When I plot them, let's see, the 30 goes next to the root 3. The 30 goes across from the 1, and the 2 is the hypotenuse. I have to make one little subtle change, though. Now that it's in this quadrant right here, this and this are negative. The reason why they're negative is because this is the positive x direction, this is the negative x direction. This is the positive y direction, this is the negative y direction. So rather than going forward and up, we're going backwards and down. So I actually have to put some negatives on these guys here. It leads to a question, well, what about this guy right here? What about the 2? We never make the hypotenuse 2. And the reason why is that when you use Pythagoras' theorem, you go negative 1 squared plus negative root 3 squared equals 2 squared. We always prefer for this to be like a positive number, the way Pythagoras' theorem works out. So you can make these numbers right here negative if you like, but always make that one positive. Okay, well, now let's try that same task. What is tan supposed to be equivalent to? Tan is supposed to be opposite over adjacent. Okay, now the angle we're talking to is all the way around to here, but really the angle we're speaking on is that 30-degree reference angle. So which side is the opposite to that 30 degrees? That minus 1 over here. Which side is the adjacent? This is the negative root 3. So this is now my exact value for tan 210. Now, your calculator has been pre-programmed to know all of these values just like that. But let's just confirm this then. If I were to type in the tan of 210 degrees, it's going to give me 0.5773 as its rounded value, its pre-programmed value. But if I were to type in -1, which is kind of silly, divide by -√3, now we know where your calculator got that value from. Calculator didn't just pick that out of nowhere. That's the value that it had been programmed to know. And this is the exact value. Yeah, you probably would rationalize it, so the more likely answer would be to call it √3/3. Yeah, you're right. Let me try some more examples here. This is one of those things where you got to bear with me for a while. I've got to show you like everything, I think, before it starts to make sense. I feel like, though, as I watched a few of you had a little bit of a light bulb moment here and there. You're like, oh, I see how this fits together. But please don't freak out until I've done all 3 lessons, okay? If after all 3 lessons you still feel like you're lost, then let's chat, okay? You gotta take off. Okay, let's try another one. Let's say the angle wasn't a degree angle, though, because we've learned now that some angles can be in terms of how many radians you have. Well, let's work with the sine of 7 pi over 4. So first question we got to ask is, what the heck is 7 pi over 4? Where in the world would that be on this grid? Okay, well, let's break things up into quarters. This would be your first quarter. This would be your second quarter. This is the third quarter. Over here, right along the axis, is the fourth quarter. That's where the Patriots shine. Okay. This would be the fifth quarter. Does that make sense? This is your first, your second, your third, your fourth out of 4 quarters, your fifth out of 4 quarters, your sixth out of 4 quarters. Here it is. This is your 7th out of 4 quarters. What's 8 over 4? Yeah, 2. 8 would be back around to where you start, which would, I mean, keep in mind, these are all out of pi, right? So this is quarters of pi. It takes a while to wrap your head around this whole pi thing. It's very strange. But this would be going all the way around the circle. So if you can agree with me here, 7 quarters of pi really means to go all the way around the circle, but like leave off a quarter of pi. Why don't we actually convert it to degrees? 7 over 4 pi. The way you convert it to degrees is you times by 360 degrees for every 2 pi. What ends up happening is this pi cancels right here, and I'm just going to just times everything else and divide. So 7 times 360, divide by 4 and divide by 2, tells me this was 315 degrees. Does 315 degrees in this quadrant here make sense? I think so, right? Because we know that this is 270 degrees right here. This is 360 degrees right here. 315, that kind of makes sense. What's the leftover bit? Yeah, 45. Hey, 45, isn't that a triangle we learned about? Okay, so I'm going to draw the triangle in a new color here first. Then I'm going to go find that triangle, and I'm going to superimpose it on top of this here. So here's that triangle. I'm going to go way back in my notes here, and maybe you have them somewhere closer. The 45-degree triangle works like this. One side is 1, the other side is 1, and the hypotenuse is √2. So I'll go back here now again. This side here is 1. This side here is also 1, and this hypotenuse is √2. Except for one thing. One of them has to be negative. It's this guy right here. Because it's gone all the way around the circle and it's back in this quadrant here, we're actually going down and over. We're going positive for x, but we're going negative for y. Okay, let's try solving this now. What is sine supposed to be equivalent to? Opposite over hypotenuse. Okay, well, for this angle right here, my reference angle, the opposite is -1, and then the hypotenuse is √2. Let's try it. Now, one thing we have to do though is we have to, like say, convert into radians. So I'm going to go to my calculator. I'm going to press mode. I'm going to put it into radians. I'm going to give this a try. Sine of 7 pi over 4. Let's see what it equals. Okay, right off the bat, it's a negative number. Does the negative number make sense? Well, yeah, because this ratio right here is negative 1 over root 2. Let's just confirm it. Negative 1 divided by root 2 is that value. What your calculator has been pre-programmed to do then is it knows the exact value for pretty much every angle it can. Does that make sense? It does it for 7 pi over 4, 7 pi over 5, 7 pi over 6, 7 pi over 7, right? And it does it for every single one. And every time you ask it for this in a calculation, it replaces it with this. Only we would rather try to keep exact values as often as we can. So that's kind of my goal. That's why the whole point of today's lesson is all about angles and exact values and kind of getting used to writing them in a different way. Okay, let's try one more. Let's try tan of negative pi over 3. Can you have a negative angle? How do you make a negative angle? You go the other way. Rather than go this way, as the sun normally goes, just make the angle go backwards. Whereabouts would negative pi over 3 be? How about this? What is negative pi over 3 as degrees? Let's try that. Pi over 3, if I want to put it back into degrees, I'm going to times by 360 degrees for every 2 pi. Let's find out what that is. 360 divided by 3 divided by 2 is 60. Actually, that kind of makes sense. How many degrees are there in like a half circle? 180. What happens when you cut that into thirds? 180 cut into thirds is going to be 60s. So we need an angle of about 60 degrees going backwards in this quadrant right here. So this is us going backwards pi over 3 degrees. Well, now I need to label the sides of this triangle. So I'm just going to go back to way back where it was right here. Look them up again. Let's see. 60 is across from root 3. 30 is across from 1. 60 is across from root 3. 30 is across from 1. 60 is across from root 3. Let me clean this up a little bit here. 60 is across from root 3. 30 is across from 1. That means that's the 2. Can you guys handle what I just did there where I went and looked at the triangle and figured out which sides go where? One more thing. One of them's negative. The root 3 is. Right? This is still going in a positive direction, but this has gone downhill. Last step. I now want you to figure out the tan of this. Well, tan is opposite over adjacent, right? So compared to this angle right here, my reference angle, which side is the opposite? Negative root 3. Which side's the adjacent? Yep. Okay. So maybe to answer a question you never asked, how does your calculator know what tan of negative 60 is? Because isn't that what this basically is saying here? Give us the tan of negative 60. I'll do it in radians still. If you ever type in the tan of some number, how does your calculator know what to do? Well, it knows that it's this number right here, but this number right here is actually negative root 3 divided by 1. I don't really need to divide by 1, but it knows to use that number. And so hopefully this kind of explains, like I said, this is a question you never asked, but how does your calculator know what to do when it asks for the cosine of 8? Well, that's essentially what it's doing. It's been pre-programmed to know what all of the exact values are. Not for degrees normally though, but typically for radians it makes more sense actually. Because you can break things always up into fractions of a radian. That makes sense? Even if it makes a little bit of sense, it's good. Because I feel like I haven't really taught you the whole big picture yet. But if you can follow that a little bit, that's good. Okay? If not, Don't worry just yet. You have a question? This one right here. If this is my angle right here, then the opposite was this side here, and that was the adjacent. You're good? Okay, last thing, and then we'll actually finish yesterday's notes. I went a little slower than I wanted to, but I wanted to make sure I was thorough. What I want to describe here is one last piece of terminology. It's called coterminal angles. We already actually kind of know this concept. I just haven't used the vocabulary yet. Coterminal angles are angles with a different measurement, but they're in the same spot. Like, for example, here, I screwed this up badly. This is the angle pi over 2. This is half of pi in radians. Well, another way that I could answer this would be to go all the way around the circle backwards and go backwards 3/2 of pi. We call those coterminal angles because they're literally in the exact same spot. We're just giving them a different name to them. Or here's another example of a coterminal angle. This is 130 degrees. I could go all the way around the circle once and then keep going 130 more. I would say that 130 and 490 are considered to be coterminal because they end up in the same spot. It's just another way of saying it. Okay. I want to show you two last diploma type questions, and then we'll move on here. So here's the first one. Which of these angles is not 150 degrees? All of these angles, except for one, are in the 150 degree spot. So let's try them one at a time here. Where would 150 degrees lie if we drew it in standard position? Well, you draw one arm along this axis, and then 150 would end up somewhere over here, I guess. And that angle there would be 150 degrees. Let's talk negative 930. What does negative 930 mean? It means go backwards around the circle. So you could try doing something like this. What if I took a negative 930, and what if I started going, rather than going backwards around the circle, what if I started going forwards the other way around the circle? So what if I added 360 to it? It's like I'm unwinding the circle. So like I've unwound it once. I've unwound it another time, but it's still negative. Let's unwind it one more time. Hey, if I unwind this thing 3 times from going the wrong way around the circle, I guess it does land at 150 degrees. Does that make sense? So this one here is indeed coterminal. Well, another way I could write an angle would be to convert it into radians. So why don't I take 17 pi over 6, and let's convert it into degrees. So I'll times by 360 degrees, divide by 2 pi, cancel pi, and let's see what it gives me as a degrees number. 17 times 360, divide by 6, divide by 2. I got 510 degrees. Well, hang on a sec. Isn't 510 degrees going around the circle too much? Okay. Well, why don't I try that exact same trick? Why don't I take 510 degrees, but rather than adding 360, why don't I unwind it by subtracting 360? Oh, hey, look. It went one rotation around too far, but apparently 510 degrees, which is 17 pi over 6, is actually in the same location as 150. It's just it's wound itself too far, that's all. What about 23 pi over 6? Could this be like going around the circle again once too many? Let's try it. 23 pi over 6 times by 360 over 2 pi, cancel the pi. 23 times 5, 360, divide by 6, divide by 2. I got 690 degrees. Okay, well, clearly, again, that's going around the circle too many times. So let's take 690. Let's unwind it. Let's take off a 360. That's not 150. Let's take off another 360. Oops. Oh, it looks like I didn't hit 150. Okay, so based on that, I guess this one must be the one that's not coterminal. Let me prove the last one to you while I'm there. What if I were to take 150 degrees and do this? What if I did 150 degrees and I times by 2 pi and divided by 360? Actually, no, let's not do that. It's not going to get me what I want. To try this one right here, why don't I convert this into degrees by timesing by 360 divided by 2 pi. This one's a bit more challenging to work with. That's why I should do this one. Do you see how this one was in fractions of pi, but this one right here is not in fractions of pi? I can still solve it. It just, I have to be a little more careful here. What I'm going to do here to convert it to degrees is, remember how this one here had a pi you could cancel as a pi? This one right here does not have a pi to cancel. So what I'm going to literally have to do is go negative 3.67 times 360, and then I'm going to divide by 2 pi in brackets. So it's going to look like this. Negative 3.67 times by 360. I'm going to divide by 2 pi. So I got negative 210 degrees. That's the wrong way around the circle. But what if I were to add 360 to it and unwind it the other way? I like 149.7. That's 150. Can you guys, however, see why this would not be preferable? So this is actually the right answer then too. Why this isn't preferable to these guys? Those guys are exact. This right here has been rounded. We hate rounding. Okay, last question. It's a long lesson. This is the creme de la creme. I'm putting it all together now. Everything we've learned, we're going to try to put into this one question here. Again, this was an old diploma question, so this applies more to the guys in 30, obviously. But like the basic concepts, I think, are really important for like you're supposed to learn part of what I taught you today if you're in 20-1, but I'm going a little bit beyond. Okay, I hope that's okay. I hope you get why I'm doing it. I'm going a little bit beyond what the actual curriculum is, but it's actually not that far yet. You want to find this exact value right here. In theory, you could just take this, type it in your graphing calculator, and get an answer. But let's try to prove why. Let's start with this. What the heck does 13 pi over 6 mean? Well, hopefully you've now learned that 13 pi over 6 is another way of representing an angle. I'm going to break a grid up into sixths. Here's my first sixth, my second sixth, my third sixth, fourth, fifth, sixth sixths of pi would be right there. Does that make sense? That's sixth. Then here would be the 7th, the 8th, the 9th, the 10th, the 11th, and the 12th sixth of pi. Does that make sense? What's 12 over 6 again? 12 over 6 is 2. Isn't 2 pi supposed to be all the way around the circle? Well, if I want 13 sixths of pi, what am I really telling you? Go all the way around the circle, and then go 1/6 more. So that means I'm looking for an angle that's somewhere in this quadrant right here. So this is what I'm asking you to do right here. Does that make sense? That's where 13 sixths of pi is. Why don't we actually convert 13 sixths of pi into degrees? Just because until you guys get more fluent working in radians, it often helps to be in degrees because you can picture it better. So if I gave you 13 sixths of pi and asked you to times by 360 and divide by 2 pi, how many degrees is this going to be? 13 times by 360, divide by 6, divide by 2. I got 390 degrees. Okay, does 390 seem logical? Hopefully, because it's slightly more than a full circle, right? If you agree that 12 sixths is all the way around a circle, 13 sixths should be a full rotation plus a little bit more. How much is the little bit more in degrees? 30 degrees. Because 390 is 30 degrees more than a full rotation. Well, now that I have a triangle here, I need to start plotting some sides. Because this is kind of putting it all together now. What are the sides of the 30, 60, 90 triangle? Uh, 30 goes across from 1. 60 goes across from root 3. 30 goes across from 1. 60 across from root 3. So 30 goes across from 1. 60 goes across from root 3. The other side is 2. Okay, so now that I know what the angle is, the next question is, what happens when you want the tan of that angle? Well, isn't tan supposed to be opposite over adjacent? What's the opposite of this reference angle right here? Okay. What's the adjacent? Okay. So that means that all of this right here, I can now replace this whole mess that I'm just going to scribble out here with 1 over root 3. But I have to times it by minus 3. So when I'm done, I'm going to go down a little bit here. It was minus 3, and it was supposed to be times tan of all that mess there. But tan of all that mess is 1 over root 3. Chances are what they did then is they rationalized. You guys remember doing this, where you times by root 3 over root 3? It ends up giving you negative 3 times 1 times by root 3 on the top. And then root 3 times root 3 on the bottom is literally just 3. That 3 and that 3 can then cancel, giving you a final answer of negative root 3, which was B. Okay. That's what I'm trying to build towards. Okay. So through a very, very long lesson, that was kind of my ultimate goal here. Okay, help me out here. Give me a thumbs up, middle, or very, very low here. How am I doing so far in terms of your understanding? So, okay, if it's not that high. Oh, yeah, it's not horrible. Okay, how about I do this here? Give me 5 more minutes, because I don't want to talk to you the whole class. Okay, give me 5 more minutes. I just want to hop ahead in the next set of notes to one of the further ahead examples we're going to do, and then I'll re-loop back to that tomorrow. Is that fair? Give me 5 more minutes, okay? Because really this is all meant to just keep going with each other here. Can you guys find this example over here? It's a long ways through there. Try to find this example here. The extension I want to finish with before we call her a day is that as soon as we start plotting things on an XY coordinate, we can then plot things as coordinate points. So here's my final example. We're going to call her quits after this one. What I'd like for us to do here is plot the point 3, 6 on the graph. So 3, 6 would be over 3, up 6. 3, 6 would be right about there. Does that make sense? What I'd like for us to do now is make a triangle using this one point. Now the rules for standard position are you always have one side right along the x-axis. We just arbitrarily decided that that's going to be the standard. One of the points always goes through the vertex, and then it always ends in a terminal arm. And so what we've more or less done is we've made a triangle that looks like this. You guys follow that? So with the point 3, 6, I've now put 3, 6 along here like this. Well, what it means then is that I can actually calculate some values for the primary trigonometric ratios. Watch this. If this side was 3 and this side here was 6, we can figure out the hypotenuse, can't we? How do you solve the hypotenuse on something like this? What do you need in order to solve the third side of a triangle? Isn't this going to be a right angle triangle? Don't x and y, aren't they perpendicular to each other? What's the other side of the triangle going to be? 3 squared plus 6 squared square rooted. I got root 45. I'm pretty sure you can reduce that, but for the sake of time, let's just leave it as root 45 for now. Okay. This is the final thing I want to show you today. We can calculate then the 3 primary trig ratios. We'll do secondary ones tomorrow, like this. What is sine supposed to be equivalent to? Sine is supposed to be opposite over hypotenuse, right? Well, what's the opposite of this reference angle right here? The opposite is actually 6. The hypotenuse is root 45. Now, if you guys recall from previous years, how do you solve for this angle right here then? How do you undo a sine? You inverse sine, which on your calculator means to do this. Go second sine, 6 over root 45. That makes sense. That's the inverse sine. If you do sine inverse of 6 over root 45, this should actually tell us our angle. Now, my calculator, though, is currently set to radians. Just for ease of mind as we're working with this, though, I'm going to convert back to degrees. Just because I think it's a little bit easier to work in degrees still. But as you get further along, by the time you're like in grade 11, we work with degrees still most of the time. By the time you get to grade 12, though, we got to phase degrees out. You work in radians exclusively. Sorry, grade 12s. Okay, so I'm going to inverse sine this now. I got an angle of, let's call it 63 degrees. Okay. I know I've been preaching all day, don't round, but just for right now, let's round that. It means this angle right here is 63 degrees. Does that seem about 63 degrees? Yeah, sure, seems about right. But we didn't have to use sine to calculate that angle. What if I were to have used cosine? Okay, well, what's cosine supposed to be equivalent to in SOHCAHTOA? Cosine is adjacent over hypotenuse. Our adjacent of the side right here would be 3, and hypotenuse would also be root 45. Watch this. If I were to inverse cosine 3 over root 45, I should get the exact same angle. Watch. If I inverse cosine 3 over root 45, I get the same angle. Which is good. It should. And I'm going to do this one more time with tan. Tan is supposed to be opposite over adjacent. What's our opposite of this side right here? 6. The adjacent? 3. So if tan is supposed to be 6 over 3, if we were to inverse tan 6 over 3, what should it still give us? 63. Let's just inverse tan 2, because that's actually the same thing. This is where I want to start moving to a little bit more tomorrow. I don't want to do any more today, because I feel like I've covered more than enough. But the idea we have next is that we can then take any coordinate point, we can plot it on our graph and make ourselves a triangle, and then using either sine, cosine, or tan, we can then inverse sine, cosine, or tan and calculate what that angle happens to be. And that's another part of this big picture here. Does that make sense? So, okay, quick summary. You guys can pack up while I talk. So, quick summary. Here's what we've covered. It's a lot of stuff, but we actually really aren't able to do much yet. Okay, which is why I just need to teach you lessons after lessons. Okay, because if I were to give you an assignment right now, I don't even know what I'd assess you on other than converting radians to degrees. We just haven't covered enough. Okay, but here's what we have covered. Okay, so first thing, you should be getting more and more familiar with putting something in standard position. Standard position means one axis along the x-axis, vertex always in the center at the origin, and then you're going to put an arm around a circle, almost like a rotating, like whatever, something that rotates, right? Okay. And now I just briefly showed you the idea that we can plot a coordinate point to figure out which quadrant we're in. That's one thing we've learned. Second thing we've learned, we can measure things in degrees, which is what we're pretty used to. But there's another way of measuring things. It's called radians. Radians is very frustrating. It takes a long time to be able to get used to me telling you 2 pi over 3. I understand what 2 pi over 3 is, like this, because I've got 10 years experience on you guys. But I'm hoping that eventually you'll be able to recognize that 2/3 of pi means, like hopefully you can kind of visualize it in your head. 2/3 of pi means this would be the first third, this would be the second third, this would be the third third. 2/3 of pi means an angle about that big. And the more you do it, the more familiar you'll get with it. Okay? It's annoying to always work in fractions of pi. Don't get me wrong, it's super annoying. However, it's more exact. It gives us better precision. That's one of the reasons why we use it. And it can help us calculate arc lengths as well, like we did earlier today. Third thing you should know how to do. You should be able to be familiar with something called coterminal angles, which means you can go forwards around the circle. You can go backwards around the circle. You can go around the circle 27 times and land here. So long as you land in the same spot, it's coterminal. Okay? For example, 1 degree is coterminal with negative 359 degrees. Say that again. 1 degree is coterminal with negative 359 degrees. 1 degree is also coterminal with 361 degrees. In one case, I went around the circle an extra time. In the other case, I went backwards around the circle. But in either example, we're landing in the same spot. Okay. 1 degree is also coterminal with something in radians as well. Okay. The final thing I need you guys to be familiar with is exact values. And it's really the only thing that we can kind of do anything with so far, and even that's pretty minimal. And that's where if I tell you sine of 30, you should start being able to replace sine of 30 with something like root 3 over 2. Or if I tell you tan of 7 pi over 4, you're going to start replacing that whole thing with an exact value. Usually it involves some sort of square root value in there. Does that make sense? Okay, I'll call her a day now because I know it's been a long time here. I think I'm probably just going to be picking this up tomorrow and then working on the next one after that. So just so you guys know work time, I haven't even put on the sideboard there due dates yet for Math 20-1, mostly because I don't expect you guys to start working on this yet. Is that fair? Maybe dabble on your old assignment on cosine law stuff if you haven't finished most of that off. But like next week is kind of the work week. This week I just need to teach you a whole bunch of stuff. And I don't really feel like until I teach you all of it that you really can really do anything yet. So does that make sense? So, okay, Joe. Oh, go ahead. Oh, okay, I'll talk to you in a second. Okay, you guys can take off then. Okay, we'll talk to you tomorrow, guys.